When we look out into space, we are not only looking at things that are far away, we're looking at things that existed in the past. For instance, the sun is about 93 million miles away and it takes light about 8 minutes to get here. Thus, when we sit down in the morning with some toast and our first cup of coffee for the day and look at the sun, we're seeing it not as it is now, but as it was when we put the bread in the toaster. Time and space are inextricably intertwined when we talk about how far away things are. This is especially true when we talk about large-scale structures of the universe. We even have a distance scale called a light year, which is the distance that light travels in a year. In more familiar terms, a light year is 9.5 trillion kilometers, or just shy of 6 trillion miles. We use the unit light year because nothing travels faster than light. It's very convenient. But it is most convenient when we talk about the size of the universe. Astronomers have determined the age of the universe very precisely. It is 13.7 billion years old. Exactly how we know this is perhaps the subject of another video, but for the moment, let's take that number as a given. If we do, we can ask a very simple question. How big is the visible universe? There are lots of tricky ways to think about that, but let's start with perhaps the most obvious. We can't see the universe before it began because, well, that's what beginning means. When the universe began, it was filled with light, which then traveled through the cosmos. And if the universe began 13.7 billion years ago, and we're just now seeing it arrive, it had to have traveled 13.7 billion light years before it hit Earth. And to make that point solid, astronomers can actually see light from shortly after the universe began. It's called the cosmic microwave background radiation, and it is the oldest thing we've ever seen. It is hitting the Earth from every direction, and it is, to all intents and purposes, a photograph of the birth of the universe 13.7 billion years ago. Accordingly, it would be reasonable to say that the visible universe consists of a sphere centered on the Earth with a radius of 13.7 billion light years. Boom, done. Except that this is completely wrong. That's one of the sneaky things about science. It can fool you if you think too fast. Sometimes you have to slow down and mull things over. And if you think about it for a moment, you'll realize that this way of thinking assumes that the universe is static, and, at least on average, distances between objects aren't changing. But we know this isn't true. To begin with, the Big Bang happened. The universe is expanding, and it used to be expanding much faster than it is now. And that means that the simple answer isn't good enough. I don't want to get too deeply into the details of the Big Bang, but it boils down to the idea that the universe was once smaller and hotter and has been expanding since the beginning. I made a video about it if you want more. And that expansion is key to understanding what is going on here. We start by imagining what the universe looked like when this microwave background radiation was emitted. It was hot everywhere. No place was special. Well, I guess one was, kind of. And that place is the current location of Earth. But at that moment, it looked like everywhere else. Now, there was a sphere centered around that point and at that time, and that sphere is the origin of the cosmic microwave background arriving at the Earth now. That radiation moved toward the Earth at the speed of light, and it took 13.7 billion years to get here. If we look at a sphere smaller than that special sphere, that light has already passed the Earth, and we can't see it. Light from a bigger sphere isn't here yet, so we don't see it either. When this light was emitted shortly after the Big Bang, this sphere's radius was about 42 million, that's with an M, light years away. Naively, you'd expect that this light would have taken 42 million years to get here, but it took 13.7 billion, and that's with a B, years to travel to Earth. And the reason that it took so long is that space was and is expanding. Now, if you think about that, it means that space between that sphere and the location of the Earth had to be expanding pretty fast. Otherwise, the light would have passed by the Earth long ago. I mean, it was only 42 million light years, and it's been nearly 14 billion years. So that sphere from which the microwaves were originally emitted also grew in size. And in the simplest calculation, that sphere would now be 41 billion, that's with a B, light years away. However, it turns out that the simplest calculation isn't quite right. You see, about 5 billion years ago, an energy field that we call dark energy became important. Dark energy is a repulsive form of gravity, which means that the expansion of the universe isn't slowing down, it's accelerating. That, of course, that means after 9 billion years of the expansion of space slowing down, it's now speeding up. When you take into account the effect of dark energy, that radius of the sphere from which the microwaves were emitted has grown from 42 million with an M light years to 46 billion with a B light years. And this highlights the confusion that arises from expanding space. We see the light from shortly after the Big Bang. It was emitted a short distance away, and now the location from which it was emitted is now about 1,100 times farther than it was. Further, when we see it as it was then and not as it is now. Indeed, remember that when the light was emitted, the conditions at the location of the sphere were the same as here on Earth. But the conditions here have changed. Instead of a bath of energy, we now have stars and galaxies. That's also true on that sphere. So if we could somehow see 46 billion light years away, presumably there are also stars and galaxies. But we don't see them there because light from objects that are currently that far away hasn't had time to reach us yet. In fact, and this is a mind blower, we'll never see those stars and galaxies. After all, they are moving away from us very fast and space is still expanding. We saw that the location when the universe was young, but we can't see them now. It gets weirder. Currently, there is a sphere around the Earth with a radius of about 15 billion light years. Objects that are now outside that sphere at this moment will never see as they look now, no matter how long we wait. I'll repeat that so it can sink in. We can currently see objects 46 billion light years away, but we see them as they were in the distant past. And any objects that are currently within 15 billion light years, we will be able to see as they are now, although we'll have to wait a long, long time for that light to get to us. And because of the expansion, it gets worse. It means that we constantly lose stars that we can see. Indeed, we lose about 20,000 stars per second. So there are stars that emitted photons at this moment that we will eventually see, but the photons that they emitted at this slightly later moment that we'll never see. One day, the expansion of the universe will make it so that almost all of the galaxies we see in our telescopes today, which I remind you now we're seeing as they were in the distant past, will slip from our view. We will one day only be able to see galaxies from our local group, meaning the Milky Way, Andromeda, and a few dozen minor galaxies in the vicinity. So that's the answer to the question. Our visible universe has a radius of about 46 billion light years, even though it's only 13.7 billion years old. But we're not seeing that distant point as it is now, but as it was shortly after the universe began. And the ongoing expansion makes things even worse. The bottom line is that if we're ever going to try and explore other galaxies, we better get cracking. Okay, so that one was something of a mind blower, but that's cosmology for you. If you like what you heard, please like, subscribe, and share. And be sure to click on the little bell icon to make sure that you get notified of every new video we post. Otherwise, you only get notified about a few. And I'm sure you wouldn't want to miss some new tidbit about physics, because of course, physics is everything.